Hello and welcome. In this video, it's very brief. We're gonna talk about factors affecting rates. Now, all of these factors come into play when we talk about the activation energy or collision theory of reaction mechanisms. But here it is before we even go into anything too difficult mathematically, all right? So first of all, reaction rates depend on temperature. Here we have an image of a light stick placed in hot water on the left, and you can see how it's bright. And then we have a light stick in cold water on the right, which is somewhat dim. When my kids finish trick-or-treating or something with their light sticks, I tell them, and they want to have it tomorrow, and I say, well, it's not going to be working tomorrow. It's going to all have reacted. But if you place it into the freezer, it slows the reaction so slow that the next day you can pull it out and it warms up to room temperature. It's kind of lit a little bit, so it does last. If you put it in cold water, the reaction takes longer. Okay? So again, why is this happening? Well, basically the molecules are moving faster and they're going to collide into each other more frequently, more often, and produce products, and the reactants go away. Okay, so higher temperature, they're reacting faster, they're going to go away just faster, okay, because of collisions. How about catching a lizard? So ectotherms are cold-blooded, and so one way to catch a lizard is to spray ice-cold water on it. It doesn't harm the lizard or kill it or anything like that. But you see, what happens is the biochemical reactions within the lizard slow down because they are at a lower temperature. And what happens is that of course, the physical creature will slow down or even freeze in place for a minute or so you can just at your leisure go in and pick it up, scoop it out of the house if you don't want it in your house or something like that. Okay, and this is from that website. Also, crickets, pretty interestingly, they chirp faster when it's hot and they chirp slower when it's cold, and there's actually a formula to calculate the temperature if you're into that sort of thing. All right. The other criteria here that affects a speed of a chemical reaction is surface area. Okay, so we've all maybe seen the Diet Coke and Mentos experiment. And how does it work basically? Well, Mentos has a high surface area and it acts as a catalyst for this reaction, right? You have dissolved carbon dioxide in water in the form of maybe carbonic acid, and that produces carbon dioxide gas and water, and the gas just shoots the soda out when it comes out. And of course, it's much more dramatic and interesting when things react very quickly or spray stuff everywhere. Okay, so this is done in the park, so it won't get a mess in your house. Okay, so another example, more chemical, that we can kind of relate to is we have this chemical reaction on the bottom of this slide, iron reacting with hydrochloric acid to produce aqueous iron 3 chloride and hydrogen gas. Okay, so you see bubbling, and if you place iron powder into, say, 1 molar hydrochloric acid, you'll see it bubble and fizz quite violently. I'm pointing an arrow to a little bubble of hydrogen gas you can barely see there. And on the right, we have a large iron rod, which, because of its surface area is very small, it's just the surface area of a cylinder, and there's barely any bubbles being produced in this chemical reaction on the right. Okay. The other thing that will speed up a chemical reaction is concentration. Okay, so if something is more concentrated, the molecules are more crowded or closer to each other. So again, they're more likely to bump into each other and have a chemical reaction. Okay, think about a crowded subway. People are just very nearby each other, so they're going to be bumping and jostling, as opposed to maybe baseball players out on a baseball field, which are very distant and far away from each other. Okay, here's a neat little chemical reaction. We have sucrose. It's this white colored thing in the beaker there. And we're adding concentrated sulfuric acid to the beaker on the left, and you can see over time how it produces this lump of amorphous carbon. This is how, back in the days, people figured out that sugars, for example sucrose, are carbohydrates because they're composed of carbon and water. You can actually see little water steam coming off of the lump of carbon there. So anyway, dilute sulfuric acid, the beaker on the right, just seems to sit there, nothing happens. Okay, so if you have a higher concentration, it's more likely to be a faster reaction. Okay, the last thing here is catalysis. A catalyst, we'll talk about how this actually works and what it actually does in terms of the energetics. But for now, just look at these diagrams here. We have hydrogen peroxide, remember, decomposing to form liquid water and oxygen gas. And on the very left, if you pour some hydrogen peroxide into a beaker, it just kind of sits there. If you look very closely, you might see some bubbles adhering to the sides of that beaker. If you add iodide, it catalyzes the decomposition or this chemical reaction to produce bubbles. And the key point here is that a catalyst is not involved in the overall balanced chemical equation, but it does something in there. It reacts and it, produces this, and then it comes off again, and it can do the job again and again and again and again. All right. Catalase is a biochemical enzyme, and that can catalyze the decomposition of hydrogen peroxide millions of times better than iodide. And you can see how the beaker on the very right is extremely effervescent. There's numerous bubbles of oxygen being produced. Okay, if you're interested in seeing more about hydrogen peroxide, check out Genie in the Bottle. Okay, just look that up on YouTube. You won't be disappointed. Here's my summary slide. On the left, we have faster reactions. On the right, we have slower reactions. So high temperature, high surface area, high concentration, and of course, if you add a catalyst, those are all going to make the reactions faster. And the converse of that is slow. If you don't want milk to decompose as fast, you put it in the refrigerator because it's lower temperature, okay? And low surface area and low concentration and no catalyst are all going to make a reaction slower. So anyways, thanks for watching. Please like, please consider subscribing, and have a great day, everybody.